Good morning, everybody. My name is Dinesh, and I'm a postdoctoral researcher with Professor Lenin Yao. And the title of my topic to talk today is 3D, 4D printing of morphing matter. So you have learned a lot of things regarding morphing matter. So today I will be covering following points. So the outline of my talk is what is 3D printing, what are the different types of 3D printing technique, and then from 3D, once we know different 3D printing techniques, we leverage or we know what is 4D printing, and then we talk about what are the factors uh, that affect 4D printing or that govern 4D printing, then what are the different materials available for 4D printing, and I will conclude my talk with what are the challenges and the future of the 4D printing. So first thing is what is 3D printing? Uh, 3D printing is a construction of a simple or a complex object in a three-dimensional object using a digital 3D or a CAD model by layer technique. It is like you print, like when you print a paper, you are doing a 2D printing. If you repeatedly print over and over again at the same place, you can generate a 3D structure. That is nothing but 3D printing. And 3D printing is also referred by different names like additive manufacturing. It is also referred as rapid prototyping, and it is also called as a layer by layer printing. Uh, in the next, we will be talking about what are the different types of the 3D printing. I will start with the first one that is called as a very popular one, a very cheap one, and used by a lot of hobbyists people for their prototyping different parts. The technique it's called as fused deposition modeling. Here, what you do, you start with the filament, and that filament is melted at the extruder head. And when it's extruded, there is a thin strands that deposit layer by layer on this built platform. And since the temperature at the build platform is different, that means it's cooler compared to the extrusion head, it starts cooling and solidifying. And when this process is repeated over and over again, you get 3D structures. Here, the different materials that can be 3D printed using fused deposition modeling is PLA, ABS, TPU, and so on. The biggest advantage of this technique is that this technique is very cost effective, and you get printed parts in a short time. The second technique that I will be talking about is called as direct ink writing. Direct ink writing is a modification of FDM where the extrusion head is replaced by a barrel or a syringe. And in this case, what we do is in the syringe, we put a liquid ink. So in the direct ink writing, it is also controlled by a computer-aided translation stage that moves in X and Z direction, whereas the nozzle moves in Y direction. This is also considered as a low-cost, high-speed, high printing speed, layer by layer process where liquid is dispensed to create a 3D structure. And here you can print wide varieties of viscosities of the liquids. And you can also make it functional by adding different functional materials, like you can make it conductive by adding a conductive filler. You can also make it luminescent by adding some luminescent particles, and also you can add functionality by adding functional additive to it. Another advantage the FDM and DIW has is like you could on demand, you can print multi-material printings. Like if you have multiple extrusion heads in case of FDM, or if you have multiple extruders, here I've shown on the right side only one. If you have multiple extruder, then you can print inks with multiple functionalities on one go. The next technique that I will be talking about is called as a selective laser sintering. So here we start with a powder. So basically you require a powder. So let's understand this technique. This technique is In this case, you have a built platform, and then over that you have a powder bed where you have the powder particles, and then you have a high power laser that is projected at a specific places where this powder gets sintered to give you a solid. And this process is repeated over and over again. If you want the structure to be built ahead, this build platform goes down. Then the powder from the reservoir, more powder is added over it. It is leveled, then further laser writes over it, it centers, and so on to generate a 3D structure. Here, by this technique, you get good isotropic mechanical properties of the material when you use this technique. And the materials that can be printed are a nylon, polyamide, and you can also have fillers like aluminum, glass, or carbon fiber filled nylon for this technique. One of the disadvantage of this technique is like the surface that you get after the printing is little bit grainy and rough, but if you can do post-processing, then you can get smoother finishes using selective laser sintering. The next one that I will be talking about is called as inkjet printing or material jetting. So in this technique, this is the modified version of the inkjet printing that we use for paper printing. So inkjet printing generally, if you are having a regular printer which prints black and white, so there you have only one inkjet head. And whereas if you are printing with a color printer, you have three inkjet heads. So here they took the advantage of that technology, and here you have multiple jetting heads here. And here the structure, the material that is used for printing is basically a photopolymer. So photopolymer, I will be talking more about photopolymer in other slides, like how the photopolymerization takes place. But let's understand only the technique here right now. So the photopolymer is jetted through these multiple heads, and there is a UV lamp that post-cure it. And here the head can be moved in X and Y axis, and whereas this is a built platform that moves in Z direction. The biggest advantage of this technique is here you get parts which have a very high accuracy and very smooth finish. And here the support material is also added. So during the printing, you can print complex structures. But after printing, you do need to remove this support structures, and the structures needs to be processed for further cleaning. Here, I'm showing a GIF in which the material is jetted through multiple heads, and the green is the UV light that shines over it. So you get your photopolymer gets completely polymerized and becomes solid using a UV light. The next technique that I will be talking about is called as a stereolithography. So stereolithography is made up of two words. One is called as a stereo and second is called as a lithography. Lithography means writing with light and stereo means solid. So basically, it means that here when you write with the light, the liquid is converted into solid. So here, in this process, the photoresist or the photopolymer comprises of monomers, oligomers, and photoinitiators. And when the light is projected, there is a selective photopolymerization taking place. And in this process, also it builds by layer technique. The biggest advantage of this technique is that you can print different structures with complex geometries without using the support materials. Or in some cases, if you use the support material, the support material is the same material that you can chop off. And here you are capable of creating geometries with very high resolution with a sub-micron precision. And this stereolithography, or I will say lithography, is divided into two parts depending upon the wavelength of the light you use. One is called as one photon polymerization and second one is called as a two photon polymerization. Let's talk about one photon polymerization. In one photon polymerization, I will be showing the light that you are using for curing. You could use a laser or you could use a projector. both of the techniques have their advantages and disadvantages. If you have using a light as a laser, here the resolution of the print will be dependent on the spot size of the laser. Here, the whole layer is not print in the one go because there is the rastering taking place, the lines are written, and so on. Another advantage of this technique is here that the build volume is very high. The second technique is called as digital light processing. This is one of my favorite technique, and I have worked a lot on this technique. So here the advantage is that here the projector, the whole layer is projected in one go. So since the whole layer is projected in one go, there is high throughput for this technique. And here the resolution is determined by the pixels of the projector. And if you want to get a high resolution, there is one disadvantage with this technique is that the build volume is lower. Now, I have used photopolymerization or photopolymers in a couple of printing techniques, so we should also understand how the process works. Whenever you heard a word called as polymerization or polymer, three things you should come into mind is like the reaction steps. That is first step is called as initiation. Second step is called as propagation. And the third step is called termination. So now let's go into details of this. When you talk about a photoresist, it comprises of three things. First one is called as monomers. Second one is called as oligomer or crosslinker. And the third one is called as a photoinitiator. I call the photoinitiator as the heart of this process, because if you don't have photoinitiator, you cannot, the resin will not undergo photopolymerization. So let's take an example. Let's say this is a photoinitiator, which is a symmetric molecule in this case. Let's say ROOR. And when I put a UV light, this bond is broken symmetrically. When this bond is broken symmetrically, you generate free radicals. These free radicals are highly unstable. Since they are unstable, they attack unsaturation places. That means the places where you have carbon-carbon double bond or carbon-carbon triple bond. In our case, we talk about carbon-carbon double bond. So once the photoinitiator free radicals are formed, they combine with the oligomers and monomers. The process starts, that's initiation, and then further it combines and forms longer molecules, that's called propagation. And finally, a small molecule is combined at the end of the photopolymerization, which results into termination of this process. And the biggest advantage of the photopolymerization is that here there is selective polymerization. That means wherever or whichever place you shine light, only that part will solidify. And this is the main basis of the many 3D printing techniques that I have talked in my previous slides. The next one that I'll talk about is another type of lithography technique that is called as a two-photon polymerization. This technique is used for printing high-resolution structures. You can imagine that the structure size is smaller than the size of the hair. The hair is around 100 to 150 microns, and here you can print structures that are in nanometer resolution. So basically in two-photon polymerization, there is a laser. It's a femtosecond laser, and the wavelength is around 780 nanometers. And then you have mirrors, and then you have focusing objectives, and then you also have a photoresist. The photoresist is similar. The only difference is the photoinitiator that is used in one-photon polymerization and two-photon polymerization is different because the wavelength of the light is different. And here, the advantage of this technique is that the smallest feature that you can print using two-photon polymerization is in order of 100 nanometers. And as I discussed, the parts that are used for this printing is you require a strong femtosecond laser, objective, and a photoresist. And you require a piezoelectric stage that controls the X, Y, and Z motion. And on the right, you can see some of the images I depicted. They are not morphing, but I just wanted to show you that how small you can go. Like here, they have a miniaturized wind turbine, and there is a cartoon image where the scale bar is around 14 microns. So these are the few techniques that are, these are the major techniques that used for 3D printing. And now what I want to do is I wanted to compare what are the different 3D printing techniques. And we wanted to know like what are the advantages, what are the disadvantages, what are the different materials, and what are the resolution that you can get. In fused deposition modeling, you could print like 10 raised to 5 millimeter cube per hour. Whereas if you talk about direct ink writing, it is also the similar speed. Whereas if you talk about selective laser sintering, the speed is 1 order higher. And for inkjet printing, it is, I would say, roughly the same speed as FDM or direct ink writing. And stereolithography is also 1 order ahead. The resolution, if I talk about the infused deposition modeling, the resolution depends on the extruder nozzle, and the smallest resolution that we can get is around 100 to 150 micrometers. In direct ink writing, the resolution is governed by what is the width of the needle that you use. So you could get in order of like hundreds of micron in this case. In selective laser sintering, also you can get around 100 micron resolution. Whereas in inkjet printing, you could get a resolution of around 50 microns. In stereolithography, depending upon which system you use, like for example, if you use 1 photon polymerization, you can get a resolution or a feature size in the range of 50 to 100 micrometers. But if you're talking about 2 photon polymerization, you could get a resolution of few hundreds of nanometers to 1 micrometers. In fused deposition modeling, it is one of the cheapest and easiest, but one of the disadvantages is like you do not have wide varieties of different materials that can be printed using this technique. In direct ink writing, you need to require ink which is in liquid state, and it should be solidified after it's getting extruded by some means. In laser sintering, you need a powder which can be sintered using a laser. In inkjet printing or multi-jet printing, the ink that you need to use is a photopolymer, but the viscosity should be very low, like 0.25 Pascal second. Since the viscosity is low, you cannot get properties of the materials, like you cannot have high elongation materials in this technique. In stereolithography, you could print materials which have a viscosity around 5 Pascal per second. The only condition required for the last two technique is that the material should be photopolymerizable, or I will say, since the lights that are used are in the UV range, I call it as it should be UV curable. And further, we could also add functionalities by adding different materials. So here I have laid down a schematic of few techniques where you can do multi-material printing. Like if you talk about, as I already discussed when I was talking regarding fused deposition modeling or direct ink write, I told that like if you have multiple extrusion heads, you could print different materials on demand. Like you can, if you want to show a color, then you can use two or more different color filaments, or you could also use two or different materials having different properties using this material. In jetting, that is polyjet, you could print a different polymers from a different jetting heads, and you can get desired functional properties. In a stereolithography, what you need to do is like here you have a resin bath or a resin, or I'll call as a vat. So here you need to sequentially change the vat. The highest number for vats that has been shown demonstrating a stereolithography is 8. I have demonstrated here, I have shown here a representative in which you are using 3 different materials. Like first you print the blue one, and then you change the resin tank to orange one, and then green one. So you can control different materials only along the z-axis. Whereas if you talk about the jetting or FDM, you could control different materials in X, Y, and Z. So FDM, DIY, and jetting is superior compared for multi-material printing compared to SLA techniques. Next, Since now we know what is 3D printing, what are the different 3D printing techniques, we should know 4D printing. So when you go from 3D to 4D, that means you are adding an additional dimension. So the additional dimension here is and time. So when you combine 3D printing with time, and if there is a change in structure or shape, then we call it as a 4D printing. 4D printing is evolution in the shape, property, or functionality of 3D printed structure with time when they are exposed to external stimuli like heat, light, water, pH, etc. What I mean is, like, for example, you have printed a flower using a material, and if I expose it to a heat and light, and if it can shrink or expand or change its shape, deform, then I call that under I termed it as a 4D printing. Here, basically, what we do is we alter the shape when we remove it from the 3D printer by an external stimuli, as I discussed. When you want to do 3D printing, you require three things. One is 3D printer, and now we all are aware of different 3D printing technologies. Second, we require a smart material. A smart material is a material that changes its shape or property or functionality when it comes in contact with external stimuli. And the third one is a well-programmed design. The next we talk about is what are the different factors responsible for 4D printing. So if you want to do 4D printing, the first thing that you need is a 3D printer. The second thing that you need is you require a programmable or a smart material. The third thing, we need stimuli, external stimuli. I categorize external stimuli into three types. One is called as physical, chemical, and biological. In physical means like if you are changing shape using light, moisture, magnetic field, electric field, temperature, or UV light. In chemical means when you add a chemical, like it can be an oxidant, reductant, or if you change the pH, that is if you change from acidic environment to basic environment, if there is some change, then it's also considered as a stimuli. In biological, you could use some enzymes or glucose. The next one that is important is called as a mechanism of interaction. That means, for example, you have also heard about 4D printing or the 4D printable materials, like you require a mechanical loading or physical manipulation. Like, for example, in the previous class given by Kerr or Gianze or Adriani, you need to like do a physical manipulation. Like, for example, you put a structure on a hot state and then you bend it and then you again put in a hot state and it comes to 3D. So you require mechanism of interaction. And the fourth one, sorry, not fourth one, the fifth one, the very important one is modeling. Here, modeling means design. Like you need to have a forward or a backward design or the production that is very important for 4D printing. Is like this point was covered very well in the previous class by Gianze, who was talking regarding like if you have different pipe lines like forward or backward, then you can always like predict a shape, or you start with a 3D structure and you from this design tool, you know what will be the end shape, or for whatever is a desired shape. From there, you can back calculate and get the initial state of the structure. The next one that we talk about is what are the different types of materials, or what are the different smart materials that could be used in 4D printing. The first one that I talk about is called as a hydrogel. As the name suggests, hydro means water. So this material is responsive to moisture or water. The second one is thermo-responsive. That means it changes its shape when it comes in contact with temperature or heat. The next one is called as a photoresponsive. That means this material will be responsive to light. The next one is electro-responsive. That means here when you give electricity, it will change the shape. We also have a magneto-responsive. Piezoelectric materials also come under this category. And the last one will be the pH responsive. Let's see a few examples of these. The first one I will talk about is called as hydrogel responsive. So here you have a material which has polymers, and it also contains high content of water. Here I'm giving an example of a 3D printed hydrogel, a flower. This is 3D printed using DLP technique, and then when you soak it in water, by time you see that it expands. Here it grows in volume. In this case specifically, it is like 7 times the original weight, and you can also have materials that can expand up to 200% of this volume. The biggest advantage of these materials are these are biocompatible. That means this can go inside the body and can be used in vitro and in vivo. This is an example of an shape memory polymer. By changing the pH conditions, it can morph into states. That is, it can bloom or it can unbloom, or I will, in the simple terms, I will say it can close. The next one is I will talking about is called as thermal responsive smart materials. These materials are responsive to heat or temperature stimuli. These materials are called as shape memory materials, and there are different types of shape memory materials. Like you have shape memory polymers, then you have shape memory alloys, you have shape memory ceramics, you have also have shape memory hybrids, and you also have shape memory gels. I will be covering some of them, not all. Here you can see this is a shape memory polymer. When it is treated to an external stimuli like a heat, it can start morphing. The first one is an example showing a stent. This is a shape memory stent. As you can see here, where it like this was printed at this state, and then it was manipulated. That means it was put to heated state, deformed, and then again when you go to gives heat, it goes to the initial state. These are pillars, and when they are treated to an external stimuli, they go to the from deformed state to the initial state. This is a dragon who is flapping a wing. And the last one, another example of shape memory polymer is the iconic monument that is Eiffel Tower. This was printed using a DLP technique. And then when it is exposed to heat, it can come to its original state. And then when it is in softer state, you can deform it in this state. And then again, when you apply heat, it goes back to the original state. Since we are talking about tangible, I was thinking to show you an example that is could be used in our day-to-day life, where, for examples, if you are talking about the shoes which are containing heels and flats. So here, this is a 3D printed shape memory polymer where it was printed in this state, the bottom right, where it can be used as a heel. And if you don't want a heel, then you just expose it to, or you just expose it to a hair dryer, then it goes to this state. So here, you don't need to have two different, I will say, shoes. One shoes can perform both function. In the state function, in function one, it will act as a heel, and state two, it will give some aesthetics like additional design to the shoe. You could also use shape memory polymers in jewelry as well. Here, Zarek et al. Has demonstrated here that you can have a customized ring where, depending upon like where if you are at home, where the temperature is little cold, then the flower will not bloom. But if you go to an external, if you go outdoor and if it's sunny, due to the heat responsive material or shape memory materials, this can bloom, and you can have two different rings on demand, where you can have bloom state or unbloom state. Next we talk about is a photoresponsive. Photoresponsive materials are the materials which they respond to light. Basically, what happens in this case is like when you project a light, they absorb light and they get heated. One of the demonstrations that you have already done in a class where you have done using a shrinky dinky material where you have patterns, and when they were exposed to IR light, it gets heated and gets deformed. So this is also a similar case where when it is exposed to light, it starts morphing. This is a flower. The next one that I have given you a small example is an electric responsive. So basically in electric responsive material, what you do is you externally apply electricity. And when you externally apply electricity, the system gets heated. Here in this case, this is an silicon elastomer embedded with ethanol. And when you are applying electricity, you are basically heating. So what is happening is ethanol is getting expanded. And if you stop the current, the ethanol will contract. And this can be an example of an electrically activated artificial muscle, as shown here. The next one we talk about is called as a pH responsive. These are very important in a biological or bioengineering field. I'm showing you two examples in which, for example, you have a star. This star is having a drug at a pH 1.2, and when it is going to a pH 7.5, it changes to yellow color because the drug loaded here is released, and also the second thing is that it expands. So you can load this type of materials with different functional things, and on demand it can change color. Here it changes color. It can also change shape, and it can also be used for delivering drug. Here is the second example where this material is pH responsive as well as temperature responsive. So here, this is a photopolymer that was 3D printed using DLP technique. This is a dry state. This is in at a pH 2, and when the pH is increased to 7.4, it expands. Similarly, there was a different formulation of the material in which if you do it at a lower temperature at pH 2 and pH 4, you could see there is a significant difference in volumetric expansion in this case. So you also have materials that are pH responsive. At a lower pH, what happens is the proton is accepted, whereas at higher pH, the proton is released. And when there is proton release, the materials has an expansion, and due to this expansion, it can intake more water, and the volumetric size increases. The next one that I talk about is called as a magneto-responsive materials. So when you talk about magneto-responsive materials, means these materials will change their shape or will move when they are they come in contact with magnetic field or magnetic energy. Here it's a blooming of a flower, and if you have a rod with a magnet or a magnetic rod, you could see that you could manipulate the position of this. The second one is a crawling board used prepared by 3D printing using a magnetic material, and here in this case it was printed in a way that the magnetic poles were aligned in different direction, and depending upon what magnetic field you apply, you can get different modes. In this case, they showed crawling, they showed moving, and they also showed rolling in this case. The next one is, since I also touched about multi-material printing, you could take an advantage of two or different materials having different contraction ratio or different properties, and you can get a 3D structures from a 2D. This is from our lab where the rose was printed flat with two different materials. One was PLA and second one was TPU, and when it comes in contact with heat, you see that it turns from 2D to 3D. This is an tense gritty bot, and it is in a collapse state. And when you apply an external heat, here in this case, they put a hot water, and you can say that its shape has changed. And once you remove the external stimuli, it will collapse. So you can have, you can consider this as like if you want to have a collapsible structure that on demand can collapse and also can grow on demand. The last part of my talk is talking about what are the challenges and futures of 4D printing. There are three things in which 4D printing depends. One is 3D printing. The second one is smart materials. And the third one is design or modeling, as I said in my previous slide. So there is a need of development of 3D printing ahead. Also, like you need to have structures that could be printed at very fast, very high resolution, multimeter scale, multi-material, and also at a multiple scale. Second, you need to have materials that are very smart. That means you could see that in some cases, like when I was talking about 3D printing, all materials cannot be printed using all 3D printing techniques. So you need to have smart materials which could be used to print in wide varieties of platforms. Second, they should be multifunctional, that if they are just not only responsive to light, if you can have a functional material that is responsible to different states, that will be an additive advantage. One of the disadvantage of these smart materials is that they degrade by time, but we need to have materials which are more robust. That means that can survive multiple cycles or should not degrade easily. And the last one is design or modeling. Like there is a need for development of multiple tools which can predict the transformation, or you could have a system in which you have a desired shape and a start shape, and if you can predict and then you design it and model it, it will be nice. In future, it has a lot of applications since they are smart and functional. There are can be used in smart and functional devices. One of the other application is robotics. And since some of the smart materials are biocompatible, they have a lot of advantages, like they can have a lot of scope to be used in body, like for example, drug delivery, or carrying some smart robots to carry out some functions in invasive surgeries and so on. So researchers are putting a lot of energy and time to strive forward and come up with smart solutions that we need. What's next? Fly with imagination and print your dreams. So basically, this is also a shape memory polymer. It's a bird. When you heat it, it can start flapping. Thanks for listening. Do you have any questions?
Thank you, Dinesh. Yeah, if you folks have any questions, so I think this is also a good summarized conclusion technical slides for our course, because Dinesh did go through, you know, some different stimuli types, potential materials, and these some of the applications definitely go beyond, you know, like the general context of, let's say, morphing matter. They are pretty much just functional materials, right?